Well, hello everyone. Thank you for joining the CTSI BERD seminar series today. This is our second seminar for the semester. And before we get started, I just wanted to remind everyone that this Zoom session will be recorded. And if you're a registered participant, you will receive a link to the recorded video as well as the slides from the speaker. While you join, you will be muted, but you can post your questions in the chat window, and also feel free to unmute yourself at the end of the seminar, or if the speaker is okay at the between the slides, and ask your questions. So today we have Dr. Timothy Brick from Penn State. Dr. Brick is an associate professor at the Department of Human Development and Family Studies. He's also a member of the ConDev methodology group and an affiliate of the ICDS. So among his wide research portfolio, he is also interested in developing statistical analysis methods and experimental methods for personalized patterns and responses. So today, I think he's going to talk about an interesting, widely being used, widely becoming popular, I think, study design, especially in clinical trial settings. So without further ado, I'll invite Dr. Brick to talk about adaptive designs for observational and experimental studies.
Thanks. Let me pull my screen share up if that's okay. Can everybody see this? Is it okay? I'll also need somebody to keep track of the waiting room and be admitting people in the waiting room.
Yeah,
I can't see the participant screen.
Okay. I got that too. Yeah.
Wonderful. So adaptive design is a really sort of complex and a broad subject area. So rather than trying to go through the entire field in great detail, I figured I'd sort of walk through an overview of the kinds of designs we expect, the kinds of designs that we've been seeing, with an eye towards sort of where I think things are going and the kinds of things that I'm excited for. And then we'll sort of build up from there. To give a general overview of the way I'm going to frame this, first I'm going to talk about the problem that adaptive designs were initially developed to solve, and the solutions that have built up from that. We'll talk a little bit more about new opportunities that those designs have developed, and then start talking about one of the places where they're just starting to be seen, which is in observational trials rather than intervention trials. And then finally, the part where I start to get excited the most, which is about within-person adaptivity and trying to take these designs to the next level. I always like to acknowledge the people who've been working with me on this, and there are a lot of them. This is a subset of the people who've been working on this kind of project with me. It's hopefully the subset of topic or project that I'm going to be talking about, but I tell a lot of stories, so we'll see if I get off topic there. Regardless, I do want to start out by telling a story. We had a study fairly recently where we had some problems recruiting. I'm sure this is nothing that's ever happened to anyone else. Especially in the wake of the pandemic, there were a bunch of insurance changes that changed our population a bunch, and we wound up with a whole lot fewer people than we initially had started with. And we had this question of whether we keep scrounging around to try and find additional funding to get up to where we wanted to be in terms of our initial our initially planned study N, or whether we stop now and just cut our losses and run. And what happened was I looked back at the way we determined that initial N, and it went through the usual process that that power analysis goes through, which is to say, we designed what we wanted to be our analysis, and then we made some lightly informed guesses from prior work and from pilot studies about every single parameter in the model that we were going to run. Now, this is a longitudinal study. There's a whole lot going on in terms of covariates that may vary within person and between person. So we had to make guesses about how much within person and between person variability there was in our outcomes, and how much these covariates captured in terms of variability. And we used that to compute an expected sample size. And then, in the process, as this usually goes, you come up with a sample size that's way too much bigger than what your funding allows. And so you panic a little bit and you go back to, the second step and say, okay, what guesses can we make? What changes can we make to the design? How can we make this so that it actually fits in the amount of money that we have? But every time we're going through this part pretty strongly, right? We're making these guesses about the model parameters based on, in a lot of cases, intuition. And in some cases, even when you have pilot data, it's not quite the same as the data that you're going to get because it's only a pilot. And so there's a lot of detail in there that you just don't know. And so my thinking at this point was, we've measured a bunch of participants already. We have really good ideas about these model parameters if we look at the data. Now, of course, the challenge with that is it's a blinded study. We can't actually look at the data. But it turns out what we can do is just calculate all of those parameters that we need for the power analysis and rerun the power analysis using those parameters. Now, as long as this is done in a way where you don't actually leak any data out that tells you something about what's going on in the data set and what's going on with your actual result, you can run this interim power analysis, and we ran some simulations to make sure this doesn't actually bias your results. You can run the interim power analysis and make a decision based on how precise your estimate is likely to be at this point, as long as you're not actually making the decision based on what the outcome is. We don't even have to worry about correcting for it. And this got me thinking, like, shouldn't we be doing this all the time? Like, shouldn't we be constantly updating these things? And of course, I'm not the first person to think about this. This is a whole field that's been going on for decades now. But this was one of the things that really got me thinking, why aren't we doing this more? And so when we look back, again, this is something that's been happening a whole lot. The challenge is that our typical study design goes like this. We develop questions, we design our theory, we design our analyses, we hopefully do our power analysis, following the procedure I said above, and then we start data collection. And then the data analysis team, kicks back, has something to eat, hangs out for a couple years while all of the people who are collecting data go and collect data. And a whole bunch of data slowly piles up in this gigantic pile in your server. And after a couple of years and a whole lot of data, you reach the end that you came up with from those probably mistaken guesses of what all your effects were. And now the data analysis team kicks in and they go, okay, now we can analyze things. And this actually leads to a serious ethical problem if you're doing, for example, medical studies. Let's assume we've got a cross-sectional medical intervention. If it turns out that our intervention is not effective and we're randomizing people away from the standard of care into the intervention, that's bad, right? Like Hippocratic Oath style, that's bad. We are actively doing harm. And if we knew beforehand that the intervention was effective, putting people into that group would clearly be unethical. Now, of course, we don't know, because if we knew, we wouldn't be doing the study. On the flip side, if it turns out our intervention is really effective, then we're in the opposite situation where putting people in the control group is unethical. And again, if we knew beforehand that we could move, like that our treatment was much, much better than the standard of care, we would be telling everybody to use the standard of care. But we don't know that along the way. If we think about this, though, what that means is, at any point, as soon as we can know what the result is going to be, right, anywhere along the way, we should stop the study and put everybody into the effective group, right? I mean, in theory, from this ethical perspective. So arguably, we should be checking our data after every participant is collected to see if we can draw a conclusion and draw a conclusion, right? Yeah, that sounds great. Of course, you can't do that, right? If you run a p-value null hypothesis test or a test against a Bayesian credible interval or any other of these binary decisions we like to make, every test has a small chance of a false positive. And when you then run a test after every participant, you start to see this effect happening, right? So this is a null effect This is a t-test run on just a sample pulled from a distribution with a mean of 0. And we're just looking at the p-value that we get if we pull one person, two people, three people, four people, et cetera. And you can see somewhere around 12 to 15 people, we have a statistically significant p-value. Hooray, we can stop, right? Our treatment is effective. This 5% risk carries an increasing chance of a false positive, and the more tests that you do, the higher the risk of false positives. And we can actually plot this out around 60 tests. It's somewhere around 98% or something like that risk that at least one of these tests is a false positive. Well, that's bad too. So we wind up in this dilemma. Now we could, right, just throw Bonferroni's correction at this. If you guys are familiar with family-wise error rate correction, right? Bonferroni is the thing everybody goes to. And we could deal with that by just saying, well, okay, now we need an alpha value of 0.05 divided by the number of people, and that'll be great. Only, again, here's that same t-test now running either uncorrected or corrected. When we do the correction, the n that we need to actually find the result, to get 80% power in this case, is much, much, much higher. And in this case is actually like the number of people, if we don't find it until the end, is actually almost 4 times as much. Or I guess 3 times as much here. That means that we're putting more people into the wrong group than we would have if we didn't run this. And so now again, we're in this situation where we've got these two conflicting things, right? I'm going to try and head off a question that almost every time I talk about this gets asked, which is, doesn't Bayesian analysis fix this? If we don't do p-value testing, can we get around this? And yeah, well, yes, but actually no. So Bayesian tools don't make binary decisions, right? The whole idea of Bayesian analysis is that you're getting a posterior probability that updates your belief about the world to something new and continuous based on this data that you've got. And so now you have new ideas of what the likelihood is, what the probability is that this treatment is effective versus not effective. And that's great. There's no type 1 error rate. We can stop that whenever we want, and we absolutely get the correct answer or a valid answer at that point. But that doesn't actually help if the FDA is trying to make a decision about whether this is an effective treatment until you make a binary decision about it. It doesn't help an individual clinician who's trying to decide, do I use this or not, until they make a binary decision about it. And once we make binary decisions about these using most of the ways that we make binary decisions, all of these problems of type 1 error and type 2 error come back. There are some ways to do this where you can make unbiased decisions. Often they hurt power a little bit because you tend to stop early, and that means you have less power when you stop. But the problem is ultimately the same, right? We're still making this binary decision, and we're wrong some of the time, and we want to be wrong less of the time. So this is still the same issue, right? And it's still this same dilemma. Ethical behavior says we should always stop as soon as we know and as soon as it's clear. And statistical rigor says, no, you can't actually do that, or all of your answers are wrong, or some high proportion of your answers are wrong. Adaptive designs were developed to target this problem. They were developed initially to figure this out and say, okay, so how do we do this right? The first set of these were called cohort sequential or group sequential designs, developed to balance these two factors. And they're mostly done using something very like a Bonferroni correction. Rather than saying we're going to measure after each individual, they build these cohorts or groups, and at certain points throughout, they're going to make a decision, right? These are decision points. And this terminology of decision points is going to be consistent throughout. We're all going to build off of this underlying idea. And so here, now we've got only 3 decision points and then a final analysis, which means that we only have to Bonferroni correct for 4 analyses instead of for 100. And that still gives us a lot of power without sacrificing some of our responsiveness. Now, we're not as responsive if we have fewer decision points, and we don't have as much power if we have more decision points. So we're trading those against each other, but at least we can balance these where we want to balance them. And all of these, in the initial years of these, the first decade or so, there's a whole bunch of these that have this same idea, right? You have some number of cohorts, you collect a cohort, you run some test, and either you continue and collect more cohorts or you stop. More decision points means that you have more responsiveness. Your cohorts are smaller, so it's every 10 people instead of every 70 people, and that means more people potentially can be put into the correct intervention, right? The more effective of the two interventions. And you're not having as many people who are at risk because of this change. On the flip side, fewer tests means more power, and that means you're more likely to actually find an effect at the end. One of the really nice things here, and looks like my image dropped off the bottom, is that we actually don't have to give every single decision point the same amount of power. And so there's a process called an error spending function. This is Google telling me what an error spending function looks like. We can prioritize or deprioritize. And the way that we do that is just by breaking up our alpha, breaking up that 5% chance differently across the different stepping stones, right, across the different decision points. So we can reserve, say, half of our power, right, a 0.025 alpha value for the end, and then split up the other 0.025 among these different points. So we maintain a family-wise error rate at 0.05, but we're really sort of upweighting our chances of finding the finding at the end, of getting a real finding at the end, and downweighting the chance that we're more responsive. We can balance these in arbitrary ways, and it turns out most of the first wave of here are 3 different ways that we can do this to improve power, or here's a way to do it to reduce type 1 error rate, are just different ways of calculating this error spending function, different ways of allocating this risk of a false positive, so that the risk of a false positive stays fixed, but we get more power in some places and less power in other places. The ballpark that I see most, and this is just me talking, this is not from, say, rigorous literature review, people tend to save about half of their error. They tend to save about 0.025 for the final analysis, and then split up the rest somehow in between. But again, that's just kind of me squinting and tilting my head to look at it. What's nice here is now we can really say, okay, we don't really think we've got good odds of finding something at the first measurement because we'll only have 40 people at that point. So we're going to check in case it's a really strong signal, but we'll only give it an alpha cutoff of 0.01 there. And then the next one, maybe we have a little bit more chance, so we'll set that at 0.015, and then the last one we'll set at 0.025, so that we eventually use up all of our type 1 error rate and therefore get all of our power out. But it's all sort of pushed to the end, and we have the most power near the end. This is a really cool arrangement in the end, and a lot of the work that's done is now done using some variation of an error spending function. Generally speaking, you're going to have somewhere between 1 and 3 of the following rules as your decision criteria when you hit each of those decision points. The most common one is a superiority rule. That is, if it's clear that your treatment already works, there's no reason to keep asking. We're just going to roll with it. This generally, if you're not correcting, will increase your type 1 error rate. And most of your corrections here are trying to reduce your type 1 error rate back to where it was. The second one is an inferiority rule, which is exactly the opposite. If it's clear that your treatment does not work, then we stop because it's just not worth looking at. And this, generally speaking, will reduce your power. And when you use both of them, they sort of balance out on type 1 error rates if you do it right, but you still can wind up losing some power in the process, again, because you're correcting so many times. The last one, which I think is really worth highlighting, is futility, where essentially you're running what boils down to a new power analysis, and you're saying, look, given the possible number of people we can get, is there any chance we're actually going to be able to tell the difference here? Futility analyses are much less common because it's rare that people want to say, well, we just wouldn't be able to collect enough people, and much more common that scientists are like, well, we'll roll the dice and see if we find something, even though our power is pretty low. That said, futility rules can be really important if you, for example, have other questions you want to ask with this money. being able to say, let's stop now and move forward with a different question can be really important. Now, I want to highlight here, these are independent of things like safety stopping rules or stopping rules for other kinds of reasons, right? So because of severe adverse events or because the number of adverse events has gone up, those are separate questions and separate stopping rules that are not related to the group sequential design. The group sequential design is really about stopping because of what you've already collected about your question, and not, oh, this study or this treatment is extremely effective, but also raises the chance that you get hit by lightning by 7,000%. Maybe we should stop this as a result of that, right? That's a different set of stopping rules and unrelated to this. Those are not efficiency rules, right? Those are safety rules and other things. There are a couple of stopping rules that you can do with almost no increase in your type 1 error rates and often very little impact on your power. The most effective of these is precision-based stopping. So stopping based on the width of your confidence or credible interval, depending on whether you're in frequentist or Bayesian land. What that says is basically we're going to keep collecting data until we know within 0.2 just how strong this effect is. And once you can say, okay, here's our precision in our estimate of that effect, then you stop, whether that precision tells you we are almost precisely 0 or tells you we are almost precisely something besides 0. Because these are not based on the actual outcome, they're based on our estimates, we sort of get that Bayesian bonus where we're only looking at precision. We're not making a binary decision based on it. And so we're in a better state to make this decision. Now, I want to highlight here, this is based on the width of the confidence interval and not the location of the confidence interval. So if you say, if you make it a decision based on is 0 in the confidence interval or not, that's just testing to see whether your p-value is significant. That's just the binary decision. You're back in the same boat. If you stop based on how wide the confidence interval is, right, or your credible interval, and say we have 95% confidence that wherever we are, we're plus or minus 3 points. That's a decision that you can make with very little increase in your type 1 and type 2 error rates. I'm not going to say no increase because it really depends on a lot of things. But these are useful tools most of the time that you can use to make a decision without biasing yourself too much. There are also other approaches if you're only doing a little bit or only doing a couple of tests. In a Bayesian world, you can use what are called skeptical priors, which are usually spike and slab type priors with a spike very close to 0. So you're pushing the model to find null results more often, and that can offset some of your type 1 error rate because it reduces the risk of you finding anything, whether it's a false positive or not. You can use regularized estimates, which also can pull estimates towards 0. You can use tighter alpha bounds, so use a 0.01 instead of a 0.05. But all of these are really fighting the same problem, right? They're just trying to balance the inflation of type 1 error rate with different approaches. And most of the time, there's an error spending function that you can use that'll do better in terms of power than using these approaches. Is everybody with me so far? Can people give thumbs up or something if they're following? Is that a thing people will do? Couple of thumbs ups. So at least a few people are following. I'll take it. If there are questions, sorry.
Sorry. No, I wanted to ask a clarification question. Is that okay?
Yes, please.
So when you do the sequential, the cohort sequential thing that you showed, is it? I just wanted to clarify. So you have the cohort 1, and then you run the interim power analysis. When you say stop, are you stopping the study, which means you're stopping recruiting any more subjects for the study, or are you stopping the randomization to the treatment or control?
So the rules are usually written in terms of stopping the study.
Gotcha.
Right? Now, from there, it's an ethical question about, well, if your treatment is really effective, do you want to recruit everybody else and put them through the treatment because that's better for them? Or do you want to just publish your results and make sure everybody else everywhere is using this treatment. Um, that's more a question of what you do with the extra money, right, and the extra researcher time, than it is a question of whether whether the process should continue. These are really written with the idea most of the time that it's like a doctor working in a hospital who has a novel treatment and is running this themselves. And so when the randomization stops, they just start doing whichever one is the better treatment. And again, publish it so that other people can do the same. Um, Again, and I want to distinguish here. When you're doing this in a group sequential design, most of the time what you're running is actually the test, your outcome test, actually the same test you'll run at the end of the study. Um, an interim power analysis doesn't give you an answer in terms of, is this effective, is this not effective? The interim power analysis tells you, okay, knowing now what we know about the actual sample and the parameters of the model, how many people do we really need to be able to get decent power on this? So in that case, most of the time it's not asking, do we need to stop? But it can ask things like, okay, do we need so many people for this that there's no way we're ever going to find a result, right? We're powered to collect up to 200 people, and the new power analysis tells us we need 1,500 to have, an 80% chance of finding anything. At that point, you want to say, okay, back up. Like, let's do something different here. But that's much more qualitative what you do with the interim power analysis, right? Where with the stopping rule, it's like if it's p less than 0.05 or 0.01, whatever, stop the study right now. This is our result.
Got it. There's also a question in the chat window. So it says, do the cohorts have to be mutually exclusive? Example, adding more people each wave to the existing cohort, thinking in terms of panel studies.
So these original designs are built with a cross-sectional view. And so the cohorts that we're talking about are not necessarily like, the first, say some class of students or some age of individuals. They're really meant to be everybody who's collected before the first decision point. So these are completely cross-sectional. It's really like each person comes in. If you have a kind of panel study where then you're running another year, there are other questions that you have to be asking, and I'll talk a little bit about that when we get to observational trials. Broadly, you should be able to do this with a panel study where you're collecting new waves of data from new people and bringing in new people along the way. But you want to account for that in your error spending function. So the Bonferroni correction assumes that all of your tests are independent, which is absolutely not the case here anyway. And most of the original corrections for this are accounting only for the fact that at time point 2 here, we're looking at data from both cohort 1 and cohort 2. And at time point 3, we're looking at 1, 2, and 3. So they're dependent in the sense that they have some of the same people. If you're using a panel study where you have some of the same people and some new people and some people are wave 2, there's a lot more complexity in how you correct for that to get as much power as possible. That said, this should work in those situations as well, because these are really built for the worst case where everything is independent for the most part. Great. Okay. Thank you for the questions, by the way. These are fun. Okay. So once we got to this point where everybody was like, okay, now we can stop early. That's great. Let's keep doing this. People kept thinking and they kept coming up with new ideas. And it opens up some new possibilities that weren't available with traditional study designs, and that can be really interesting. One of my favorites is response adaptive randomization. In an RAR design, rather than just making a single decision that's like, okay, this one is more likely to be, or this treatment is likely to be ineffective, we're going to stop everybody all at once, we do it incrementally. And so at every measurement point, at every decision point, we calculate the relative effectiveness or the likelihood of effectiveness between the branches, and we adjust randomization so that more people are going into the more effective arm. So if you can, to think of this, or to walk through this a little, we have an initial study where we've got our randomization group, our treatment group and our control group. And we randomize them at 50-50. And at our first decision point, after we've collected a quarter of our population, or a quarter of our sample, we see that the intervention group is doing twice as well on average as the control group, and we've got a certain amount of certainty for that. So in the next phase, we randomize 75% to the intervention group and only 25% to the control group. Because we still want to draw inference about this, we still want to make sure we have both groups, but we also want to give people the best chance of success. And so we move more and more and more people over into the more effective arm of the study. And then eventually, in theory, then we stop the study and everybody goes into the effective arm, whatever that is. This has some problems with traditional analysis. And so you've got to do some correction to this in the statistics to be able to account for the fact that, you know, your control group is dwindling, for example, over the course of the study. It also raises some really interesting problems when there are history effects. So for example, if you're already at the point where 80% of people are going into one arm, and then the pandemic hits, now you have the risk that there's differential differences, right? That is, that the change the pandemic has influences one group more than the other, and now we have to deconvolve those again. And sometimes that may mean dumping more people into the control group so we get a better estimate of how effective it is post-pandemic instead of pre-pandemic. There can be a lot of complexities in these analyses. There can be a lot of complexities in this kind of thing. And so there's often special handling. And it's especially the case when the probability theoretically goes to 99% or something like that, and then there's nobody in your control group. And now any history effect, any event that's happening that potentially changes outcomes, is only going to affect one group. And so often there is a ceiling and a floor, right? We say we're going to stop at 80% in one group, 20% in the other group. Or once we hit a certain level of certainty, then we just stop the study and use an early stopping rule and an early stopping approach. Again, there are some potential problems with these designs that mostly have statistical solutions, but things like history effects you really have to look at closely to make sure that other forms of validity are still being upheld. Taking that idea, you can put these together into multi-arm trials. And so MAMS trials, multi-arm, multi-stage trials, use not only this RAR approach where they're randomizing into different arms, but also they start with more arms than they need. And then as time goes on, the number of arms starts to cut down until they wind up with only the most effective arm. This is done a lot with what they call seamless phase 2, phase 3 trials, where in phase 2, you're doing efficacy and dose finding. And so you try 12 different doses and you've got 12 different arms, and it runs for a little while. And at every decision point, you drop the least effective arms until you settle on a dosing schedule that's most effective. And then essentially phase 3 is the comparison of that to the control group. This can be extremely efficient relative to running independent trials of each one, because all of a sudden you can use all the data from the phase 2 in your phase 3 for the arm that's most appropriate, and you have more comparison groups to be able to say, well, how effective is this really, right? How much does this really work? Oftentimes these are stopped with inferiority rules and superiority rules, and now the inferiority rules get more complicated because it's not just, okay, is dose size 2 better than the control, but also is dose size 2 better than the control and also better than dose size 1? Or should we be rolling dose size 2 into dose size 1 or into dose size 3? And so there's a little more complexity in those decisions, but you can think this through and sort of walk through pretty easily, like the different cases that you'd have to deal with in dealing with one of these. An increasingly popular approach is called a platform trial. Octopus trials is another name, or one particular platform. Platform trials use a single common experimental process. And when I say process, I'm really talking about the randomization process here, to compare a number of different treatments, sometimes in very, very different domains, to a set of relatively common control groups. Basically, this is a MAMS trial where you can spin up new arms anytime you want to. When you come up with a new idea, come up with a new question, you can add a new arm to the trial, study it for as long as you need to until you find an answer, and then close it down and have a result. Oftentimes these have a common control group, and there are, other variants that are multiple control group or longitudinal control group designs. These, again, can be really, really efficient in putting a lot of treatments together with a lot less effort, because you just don't need as many people, you don't need as many independent randomizations, you don't need the whole trial process to spin up independently for each of these studies. Now, the flip side of that is the platform itself tends to be pretty complicated, right? And whatever it is that you're using as this tool to keep everything together and to keep track of everything, it requires a lot of work to make it work right. There are also a lot of concerns that start to step up at this point in terms of things like data exhaustion, which is to say, if we have one common control group and there's always the chance that our one common control group by random selection happens to have only people over the height of 6'3", and with BMIs less than 15, and that means all of our comparisons are biased by the selection of that common control group. So there's a lot of checks that tend to happen to make sure that the control group is representative of the population, and also that the other arms are representative of the population. So that the control group really serves as a population control and imitates the population as much as possible. Again, these trials are really neat, and they can be done very, very well, but they require a lot of infrastructure to make work. You can't just show up and say, hey, we're going to do a platform trial with 12 different arms. Let's go. Right. There's a lot of planning and a lot of pre-design that has to go into these things. I want to also highlight here, anytime you're starting to put these pieces together, because a lot of these are combinations of different things, you want software support for this, and you want to run some simulations to figure out if you're going to wind up with biased results before you run it. And there are a couple of pieces of software to do it. They're linked on one of the slides. I think it's later in the talk. But the adapter package for R, adapt R, because R, and the Octopus software are really good tools to be able to do these analyses and say, okay, I want response adaptive randomization and an early stopping rule that looks like this, and here are these other pieces that I want to add, and have it run 10,000 simulations for you to say, okay, this leads to this much bias at these various points, and here's how you correct for that. So please make sure, if you're thinking about running these, that you dig in and really do some pre-simulation to make sure you're not going to bias things before you move forward. Any questions here? I'm going to move from here on to observational trials. So if there are questions, now's a good time.
I have one.
Yeah.
So the response adaptive, I mean, originally when I saw the name, the title, I thought it's that, okay, I'm in a treatment group, but now I'm not responding to the treatment that you're giving me. So you are changing my treatment group to the other option that you might have. Say I'm in the control, I'm not responding, so you move me to the intervention group. Is that something? Okay.
That's a smart trial.
Okay.
We're going to get to that in just a minute.
All right.
So response adaptive randomization is about the population level,
Gotcha.
the population response, and it adapts randomization of new people. Again, thinking in a very cross-sectional way into different arms. A SMART trial, a sequential multiple assignment random trial, is built exactly the way that you're talking about. We randomize people into the two groups, or into however many groups, and if they turn out to be non-responsive, by some definition of non-responsive, then we switch them, right? We re-randomize them into a new treatment, right, or an added treatment, right? We either re-randomize into the same or a different one, or if they are responding, we can potentially randomize them into different groups. So in this case, they're looking at an added boost. I don't remember exactly what the booster in this case is, but so we add coaching as an additional piece. And again, we randomize these groups separately. This winds up with a lot of different conditions in the end, because people have traveled through a variety of different paths. And if you have 5 treatment arms, it gets to be a lot of conditions.
Yeah.
But the analysis actually works pretty well. Smart designs are shockingly easy. Like the randomization process is shockingly easy given the complexity of the design.
Gotcha. All right, thank you.
Thanks for the segue. But so one of the big questions is before we get into smart designs and within person adaptivity, one of the big questions is, can we adapt these for observational trials? And of course, the answer is, well, sure, why not? There's not a lot of this that's done, but there's no reason we shouldn't take advantage of these tools to be able to do what we want to do. So there's no control group comparison, right, that we can use as our stopping rule at each of these decision points. But we're still looking for an effect, and we still can compare that effect to 0 or compare it to whatever our null hypothesized value is at each of these decision points and decide whether or not to stop. We don't have different study arms, but often we have stratified randomization, and we have different randomization groups or different subgroups of interest. And rather than adjusting randomization, we can adjust recruitment to try and upsample the particular groups of interest. Again, this has statistical implications, and we've got to pay attention to those statistical implications. But it's still, they're still possible, and it's still very straightforward to do those corrections. One of the things that I've been shouting about a lot is there's no reason that early stopping can't turn into early switching, which is to say why we can't, for example, a longitudinal design, start focusing participants on a different observational aim instead of focusing on, for example, the relationship between positive affect and well-being, or and craving. Say, let's look at the three-way interaction between affect, well-being, and craving. Let's see what negative affect has on craving, on outcomes, or on well-being. And we can do that by changing out which questions we're asking partway through the design, right? Essentially, we're stopping one design and starting a new design, but we can change this question by question by swapping out what we're asking, what we're focusing our attention on, where we're putting our energy, and more than that, where we're putting our money, right? That is, which questions are we asking? Which codes are we pulling out? What are people looking at throughout all of this? And in that sense, the different assessment foci can be different arms in a MAMS type study, where as we understand what's happening in one place, we can close down an arm and stop asking those questions in favor of asking other questions. I will say, again, this has not been done very often. This is not something that a lot of people do, but there's a lot of opportunity for it. Again, in this particular case, you really want to be sure that you're running simulations before you make these changes, because especially if you're collecting more data about, let's say our outcome is well-being, we're collecting data about well-being through the entire study, and we're collecting data about positive affect through half of it, and then we switch over to negative affect. Those changes have big impacts on the way that we do the statistical analysis. So we have to be careful along the way that we're not inducing bias. And again, I want to put a shout out for the adapter and the octopus packages, because these are really useful ways to do these rapid simulations to be able to tell what kinds of adaptive tools will influence your outcomes. More exciting in terms of observational trials is within person adaptivity.
Tim, there is a question. Yeah, I think it's relevant to the previous section. So,
sure. Any ideas on how to adapt these contexts, if possible, to a retrospective secondary data analysis? That's a really interesting question. My inclination is to say probably by the time it's a secondary data analysis, like by the time you're actually looking at data that's already been collected, the chance for adaptivity is already gone. Now, to flip that a little bit, it absolutely is possible while you're collecting the data to make some adaptations to improve secondary data analysis. And again, that's just by keeping track of all of your aims and making those decisions on things that might be secondary aims rather than primary aims. But my guess is once the data is all there, there's going to be very little benefit to throwing some of it out. And some of that is just my gut response as a statistician. being like, no, don't get rid of data. But also, I'll have to think a little bit more to see if there are any situations where it might be really useful to upsample or downsample. You use somewhat similar approaches when we do, when we do subgroup analysis, where we look for sort of a promising signal and then we dig down deeper into one subgroup or another. And in terms of developing the next study, design-based research is really built on this rapid iteration of taking a look at data that's already there, building new ideas, testing that, then looking at that data and moving forward. But in terms of just pure secondary data analysis, I think it's probably limited. That's my guess. That also makes this research really annoying because I have to collect my own data to be able to ask these questions, and I can't use somebody else's unless I'm doing it as a simulation, essentially. So probably you have done some with in-person adaptive designs if you've been working in this field for very long. Survey skip logic is really just an adaptive design, right? We're moving based on the answer from one thing or to one question, we're moving to a different question, and we're not putting attention into one thing. What we're balancing here, rather than recruitment time and recruitment effort, is burden on each individual participant. And we're balancing that burden against the value of the data that we get, right? If you tell me you're a non-smoker, the number of cigarettes I get or that you smoke every day is probably low, right? There's not going to be a lot of information in that. And so we don't ask you that question, right? Instead, we want to ask you something else. We want you to focus your energy somewhere else. Another similar one is computer adaptive testing, which follows a fairly similar process. In computer adaptive testing, you pre-rank the questions in terms of difficulty, and then after each question, you pick the next question so that it's as close to the person's skill level as you can get, so it's most distinguishing. This is kind of flipping the RAR design, where now instead of randomly selecting new participants into a treatment group, you're randomly selecting questions for an individual. This is often done in education, right? Like the SAT famously made a jump over to adaptive testing. And it has all the problems that RAR has about the first part of the questions having more impact than the later parts of the question or the later part of the study, because the randomization starts to kick in and starts to striate, and you have to pay attention to that when you're doing your analysis. Also, there's I think it's a Dutch group called, or running a study called Math Garden, that then uses, the reason I have chess here, it uses the ELO system for chess grandmasters to rank people and questions simultaneously, and try and point people to the questions that are going to be most useful. Again, this is a balance of participant burden, right? This is how much the person has to do to get a valid answer out against the value of that question. And so we're hitting the same kind of balance, except now it's at the within-person level. One of the processes that's become very popular in the last few years, Billy Namshani has been driving this really strongly, are called just-in-time adaptive interventions, JEDIs. JEDIs are interventions or assessments that are activated by certain conditions. And so this is an example from some of the craving work that we've done, where we're looking at a couple of different triggers for intervention. In this case, we check to see if the person's in a certain risk area, that is, they're within a certain number of feet of an alcohol serving establishment, for example. And then if they're showing activity, either in terms of heart rate variability or electrodermal activity or something else, then we either trigger a craving questionnaire or we don't, right? Most just-in-time adaptive interventions right now are messaging interventions. So if there is an intervention, the intervention would be something like, hey, you're at a bar with a bunch of people and you're feeling stressed. Now might be a good time to leave the bar. Things like that just nudge people to do what they're supposed to do. The Heart Steps intervention is a great example of this. It uses wearables and just delivers messages like, hey, go for a walk now. You haven't walked enough yet. These kinds of things are shockingly effective. And again, they save a lot of burden on the participant because they're not getting this, they're not just getting told every day, hey, go for a walk. It's only when they need it, right? We're not getting craving assessments just every time somebody's, or every 4 hours. We're getting it when they're in a situation they're likely to be experiencing craving. We have one of the designs with Sunny Bai. We're looking at parents and kids, and we track where their phones are, and when their phones are near each other for a certain amount of time and then split, we ask them if they were near their parent or near their kid and what they talked about, if they talked about anything. And it helps us deliver those interventions or those assessments right when they're needed. These are really fun, and they're actually shockingly easy to do. The corrections for the analysis just have to take into account the differences in timing, as long as the structure is fixed. So of course, the next step is when the structure isn't fixed, then there's lots of other things to do. This is some work from Laura Bringman. There are a bunch of other places that we're seeing it. They measured affect and measured both people's responses, so people's affective responses, and their psychiatric symptoms. And they built individual networks for each individual, like for each person in the study. And then they tried to use those to develop interventions just for that person. This is what's called a human in the loop design, or an N=1 adaptive design. It's really tough to draw population level analyses, but it's really, really useful as a means of delivering an intervention that's going to be very effective for that individual. And one of the things that you see popping up are a lot of smartphone apps that claim to do this and have no research backing that anything that they're doing is actually effective, because it's really tough to do population level analyses of these data. Right? Effectively, you're doing an analysis of whether individualizing the effect or individualizing the intervention is better than not. And it's tough to distinguish that from spending lots of time with your doctor is better than not. So, there's some real challenges making this population level. That said, smart trials are one way to do it, where we systematize the set of interventions that we have, and we keep trying, basically, until we get one that works for the person. And smart designs are a really useful way to sort of split the difference between these human-in-the-loop designs and designs that you can actually draw inference from for the population. Oftentimes tailoring it, variables, so other information about the individual, ranging from demographics to genetics to their personal preferences or history, can be used to help bias these randomizations to get people into better groups first, as long as you model it out on the other side. The new hotness, and Susan Murphy is driving this in a lot of directions, are micro-randomized trials. This is sort of a combination of a JIDI, or an adaptive intervention, and a smart trial, where instead of randomizing at random blocks, every time you might do an intervention, there's a randomization choice to decide either whether to intervene or how to intervene, right, among several arms. That randomization is done for that individual, and then the next decision point, it's done again. Again, this is a great design that lets you do within-person randomization that's really focused and really individualized. If you're willing to make a lot of assumptions about how effective these interventions are over time, you can do these with multi-level models with some very simple modeling. That is, you have to assume that if we intervene today, that doesn't affect either what happens tomorrow or the effectiveness of a different intervention chosen tomorrow. And if you keep them simple, you can still account for those. Reinforcement learning models then essentially do response adaptive randomization within the individual and change randomization probabilities so that they're more often randomized to the more effective designs, right, to the more effective interventions. Analyzing that data is a beast. And I'll point you to Walter Dempsey's work, where he's basically running Bayesian models to condition this outcome on everything that's happened so far as a starting point for that. They're really intricate, but they're really useful. I'm running low on time, so I want to jump to one last thing. There's a big question about why we aren't doing this. One of the big issues, of course, is people don't know how to do it. And so without easy access to tools, it's just tough to do. People are also, I think, very concerned about the biases that can enter. And one concern that always has to be raised when you try one of these designs is the complexity that this adds worth the benefits that it gives you? That is, all of this complexity leads to lots of problems, lots of possibilities that you coded something wrong, that the decision process is made wrong, that the analysis goes wrong in some place. There's lots of little errors, little risks that can pop in because of the complexity. There's also a bunch of big questions, right? One of the biggest ones that I run into when I talk to people about these designs is like, how do I explain to the NIH what I'm doing? And if I stop halfway through, what do I do with the rest of the money? And this is one of the reasons that I've been pushing more towards switching designs, so that when you can stop aim 1, you start aim 2 right away with that money, and just move forward. And if you get an aim 4 in, that's great. People are also concerned about what happens if the futility rule triggers. That is, if it turns out that we do not have the end to really find this, do we just have to stop and give everything back? And then I think secondary analysis is really important, right? If we're stopping collection of some things, we're making it more difficult for somebody later to say, oh, you didn't check whether this relationship affects that relationship, because the data are different than they'd get from just a standard randomized design, right? There's more complexity in it, and they have to model that out in later steps. So I think these are all big concerns and big questions, but I do think there's a lot of opportunity here. I will leave you with that since I'm right up on time, I think, but I'm happy to answer questions if people have more questions.
I just have a question. The Bringman paper for the N of 1 adaptive design, what is the first name on that author?
Oh, sorry, that's Laura Bringman.
Laura?
Laura, yeah, Laura, Laura. She has a couple of different papers that use designs like this, where they're really trying to help people at an N of 1 level. She also has a lot of really interesting work on network analysis, but that's sort of separate. These slides will be available for everybody who's registered. If you're not registered, email me, I guess, and I can send it to you. So if you're interested in that, I believe the recording will also be available for people who want to look it over.
Yeah, so for every registered participant, you'll receive a link to the a feedback survey, to the recorded Zoom presentation, as well as the Timothy slides.
And then I'm always available to answer questions if you have questions that follow on from there. I've been playing around with these models now for a while. We have a platform that does pretty well at running a lot of these studies. So if these are things you're interested in, please reach out, and I'm happy to help you out where I can.
Well, do we have any other questions for Timothy?
Okay, well, thank you all very much.
Thank you very much. We appreciate it. It's a great talk. Thank you. Thanks, everyone. So we will see you in the next BERD seminar. Have a good rest of the day. Thank you. Bye.